Okay. Yeah, I'm sorry, guys. I think we're not really late. We started exactly on time, but I stepped out to get this delivery today. For those who are watching us recorded, this is basically from Amazon in the local market in here, at least in Home Depot and what is the other, Lowe's and all of that. They don't carry high gauge wires. High gauge meaning that they're uh, 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 super thin and light, and you need those to make for solenoids, for motors, for all kinds of devices that require basically stuff that's needed for actually for the DC motor that we're going to need later on for the lab. Anyway, so I had to order it. I ordered it yesterday and it arrived today from Amazon. I'm still waiting for something else actually from Amazon in order to do some more stuff with this one. I have my what is it? The breadboard for my lab. Actually, I have one. It's attached to the Arduino thing, and I have actually another one that is not attached. I have two of them, and I have an ammeter in here. And I was running the entire experiment over the weekend, and this is my DC battery. This is a 9-volt battery, and I wasn't getting high enough currents. As a matter of fact, the ammeter in here was not recording any kind of reading whatsoever of the current. It turns out the when I connected these things on the diode lit. So there is a very weak current, and that's not strong enough to generate powerful enough magnetic fields to basically crank the whole thing and start it going as a motor. So that's really the setback that I had over the weekend because the wires were too thick. So I ended up ordering a multimeter, which we have laying around, a bunch of them everywhere in the lab, in the actual lab, because I don't have access to them. In order to also, because my eyes are not doing so well, I have a resistor in here, and I can't see the color coding in here. I think this is a 1 kilo ohm, but with an ohm multimeter, I will be able to basically decide exactly what resistors I have and all of the components that I will need for the lab. Anyway, so there is a hiccup in terms of the lab. So we're going to have the lab session. We're going to talk about the things that we can do and we cannot do, but you're going to wait for the lab instructions to be finished and completed, and that way you will complete your lab. That is the whole purpose of the whole delay that I ran into over the weekend, and I'm discussing that with you guys to make sure that you're aware of what's going on. Unfortunately, this is some of the things that can happen with the weekend. This is actually not producing a delay for you guys only, but I have another class also that I'm teaching, which is Physics 11, which is pure lab class for another class. And they also are waiting for their DC lab instructions too, so that they can start working on their lab. So this is a delay. Hopefully it's going to be overcome by Wednesday, no later, and you should be on track to doing your labs. Also, I think in terms of the exam, I graded it. There are a couple of people who I think I need to talk to. Actually, there are 3 people that I need to talk to, and I will send them individual messages concerning that. Overall, the grades, I think, were a lot higher than the first exam. That is expected, actually. This is not something odd. This is typical of how physics 4B sequence goes. Because the second part deals with the circuits, and people tend to do better in that section than with the first one. Now, the third exam also is of the same caliber in the sense of the first exam, because of the fact that it also, you're going to be calculating fields, magnetic fields though, unlike the first one, which was dealing with the electric fields. Okay. If you have some concerns about an exam, and I know one of you already requested that the student wants to see the solution for a specific problem, which is fine. I can share with that student the solution. But if you guys need specific questions, please delay those things later on, okay? So that we, at least on a one-to-one basis, so that we don't take more of the time class, okay? Any questions before we delve into finishing chapter 28 that we started on Wednesday? No? So let me share the screen with you if I can find where my notes are. They're here. So this is what we did so far with chapter 28. We covered the nature of magnetic field. Basically, I don't know if I did that or not. Basically, you need a compass to determine the direction of the magnetic field. Okay. The magnetic field. I have a bunch of magnets in here that you will need them for your lab. I have this cylindrical magnets. They're all color coded. I also have horseshoe magnet, and I don't know where they are right now. And they're actually colored in here black and blue and red. Okay, for your convenience. And I have a horseshoe magnet, and I have also a bar magnet. Those are permanent magnets. Today, if there is time, we probably are going to demo the electromagnet, which is a different concept of magnet altogether. This is not a magnet whatsoever. I mean, this does not, for example, attract any metal to it. So this is again part of the discussion of the magnetic field from the previous chapter. I'm looking for something. I'll use this one. This is a paper clip that I took basically and I destroyed, but it's not attracted to this is copper basically. It's not attracted to copper whatsoever because copper does not have magnetic properties. But when I connect this to a battery, there will be current running through it, and we should be able to find the magnetic field it produces. It's going to produce a magnetic field, and that is part of the calculation today that we're going to do. And that is part of this section in here. Okay, so this is the thing that we should be able to do. So I'm going to connect, this is a 9-volt battery that I have it conveniently connected with both poles. I have the positive on one side and the negative one, and this is the negative and the other one is the positive. The red one is always positive. The red one is the cathode. I'm sorry, the red one is the anode and the black one is the cathode. So once I connect that, it becomes magnetic. So we need to find the electric field, the magnetic field that it produces, of course. So, okay, let me see if I can get this wire connected. Okay, I think it is. And I need a, can I? Yeah, I don't want this to be in any specific shape to make it easier. Okay, you guys are enjoying yourselves, aren't you? All 10 of you watching me here struggle with these things. Had we been in class, you would be doing these things. So you're getting away with a crime. Okay. So I have the paper clip basically, which is iron mainly. And again, it's not attracted to this one since there is no current in it, and that is part of the calculation section 25.8. Now I'm going to connect the battery in here. I'm not going to measure the current because at this point I don't really have anything too significant to, oh man. It's not staying in. Okay, so right now, if there is a current running through it, it should be attracted to this thing in here, okay? So it's sticking to it because, okay, because it's a magnet now, it's magnetized. So the purpose of today is, and you will see that the magnetic field will be the strongest in the middle, right in the middle, smack in the middle. So that's really the purpose of the calculation. And it's going to be proportional to the number of turns in here. Okay, so it's sticking. So the minute I cut off the current, let me cut it off first. Sometimes these things are loose. The minute I can disconnect the current, this should not stick to it. Okay, man, I don't have enough stuff in here. Any questions? I lost my paper clip. No? Okay, so let's continue with the calculation that we started last time, or at least the stuff that we need to finish for this chapter. So we're going to have Y wires carrying the same current will attract, and wires will carrying opposite currents will not. As a matter of fact, we're going to find the force of two wires, okay? So we're going to go into interactions of two wires. So what I have in this case in here is, for my calculations, I have two wires. Remember, I just computed the magnetic field produced by a single wire. We just did this on Wednesday. So a wire having current in it running in this direction, for example, will produce a magnetic field that is given by the right-hand rule. In other words, a magnetic field will curl around. So on this point in here, the magnetic field is actually coming out of the surface, the screen, and in this region, the magnetic field is going into the screen. And if this distance is r or y, the magnetic field is going to be in magnitude mu naught times the current divided by 2 pi times the distance, this one. But this is going into the picture because think about it. The current given by the right hand rule also, the magnetic field, the current is going up with the thumb. How the magnetic field does, it curls around the thumb, following the palm, how it goes around the thumb. Okay, so if I took the current going down, this is again from Wednesday, then in this case I'm going to go like this. The current is going down, so that means in here the magnetic field will be coming out, and in this region it's going to be going in. This is the result we found on Wednesday. So today we're going to continue with the discussion, having two wires, okay? And for the initial state, what I'm going to do, I'm going to actually assume that the two wires are going to be in the same direction. So I have in here wires, okay? Oh man, it's supposed to be, okay, doesn't matter. Anyway, so I have a wire in here with the current, let's assume, in it going up, and another wire where the current also is going up, okay? These wires are long. So I'm going to assume a portion of this wire, it doesn't matter, so I'm going to take an L portion of this wire, but I'm assuming that L is big in here, okay? If I want to find the force, so this is wire 1, this is wire 2. If I'm going to find the force exerted by wire 1 on wire 2, I need to find the magnetic field in this point created by wire 1. So I need to find in this region how much the magnetic field. From the previous rule that I was talking about in terms of how the magnetic field is created, it's going to wrap around in this direction. So on wire 2, the magnetic field produced by B1 in this point, by the wire 1 that is going to be inward, going into the screen. And if I assume this distance between the two wires is d, then the magnetic field B1 is going to be simply equal to mu naught. So this current, let's take it the I1 to make distinction between the two currents so that I don't have the product, so that I can see clearly which one is which. So the magnetic field produced by I1, by the current I1, is going to be given by mu naught I1 divided by 2 pi times the distance d. This is followed immediately from the result we found on Wednesday. Mu naught times the current divided by 2 pi times the distance. So in this case, this is how much the magnetic field produced by wire 1 in the location where wire 2 is running, okay? Then we learned way back also that the force exerted on wire 1 of length L, or wire 2 exerted on wire 2 in this case, so F on wire 2 due to wire 1. So this is on wire 2 due to 1. Okay, that's my notations in here. Is equal to the current running in wire 2, which is I2, times the length of wire 2, which is L, times the magnetic field in that point, which is B1. So this result, we found it in chapter 27, actually. From chapter 27, we found that if a wire has a current running through it, it's going to be subject to a magnetic field. This is tau calculations from the previous chapter. Okay, this is again not the calculation that I'm looking for. This is tau. So the velocity selectors. There is a result that we did way back when we tried to find the magnetic field on a wire. Now this is actually the cross product, and that is not the discussion. We did the wire, didn't we? Does anybody remember that result? I see it in here, IB times L. So we have done it. That's part of the applications that we did actually together. So this is the force on a wire, okay, that we did in chapter 27. So right now we're following on that result, trying to find the force exerted on wire 2 due to wire 1. Well, wire 1, what it does in this case, it provides for me a magnetic field, that's all, okay? And the magnetic field I was able to compute from the previous calculation, which is just mu naught times the current that creates the magnetic field, which is I1, divided by 2 pi times the distance between the times where the location is. So this is basically the result that we from the previous calculation. Now the force on wire 2 is going to be just simply equal to I times L times B1. If I sub the value of B1 in this case, is going to give me basically how much the force is going to be. So the force on wire 2 due to wire 1 is simply equal to I2 times L. L is the length of a wire, okay? So that depends on that. And this force is going to be on Newton times B1. And B1, I just said it's mu naught I1 divided by 2 pi times the distance between the two wires. In other words, this value is equal to L times mu naught times I1 times I2 divided by 2 pi times the distance. L now is a characteristic of how long this wire is, okay? It's very important in here to note that the longer the wire, the greater it's going to be subject to. So there is a unit. So instead of using this force, we're going to use the force per unit length. So this is the force on 2 due to 1 per unit length. By definition, it's F21 over the length that we took. So in other words, the unit for this guy is not going to be in Newton, but rather it's going to be in Newton per meter. So this is going to be some sort of a force density, linear force. Okay. So by definition, it's the force on 2 divided by L. And this then becomes independent of that length. But note, the unit for this one is not Newton. This is Newton per meter. Okay. So this is a result for the force on a wire of two wires separated by one another. Now, which way this force will point? That's a critical thing in here. Now, the magnetic field, I mean, the current is going upward. So that's the direction of IL in here in this calculation, because this is actually cross product. So this is IL pointing upward. The magnetic field is inward, going into the screen. So the force must be pointing then this way. So this is the force on 2 due to 1. So these two wires seem, at least wire 2 is coming toward wire 1. Let's look at it now from the vantage point of wire 1. From wire 1, this is what this wire 2 will create. It's going to create a magnetic field actually in this location coming out of the screen, again, just using this rule. So if I go, now I'm on wire 2. So this thumb now is indicating where wire I2 is connected. So I2 is going up. The magnetic field now curves around and following the palm. So in this case, in I2, the magnetic field is actually coming out of the screen. But the value for that magnetic field due to wire 2 is B2 is equal to mu naught times I2 divided by 2 pi times the distance. Okay? Because what created this magnetic field is wire I2, not wire I1. So now I want to know the magnitude of that force on wire I1. So what I'm going to do again, I'm going to take a specific length in here, a length L, okay, of this wire. And I'm going to apply the same law that I just applied. So F on wire 1 now due to 2. So this is on 1 due to 2. This force must be equal to I1, because there is a current running through it at I1, times L that I took, times B2. Again, if I sub the value of this expression, it's going to be identical. So F on wire 1 due to 2 is going to be equal to, again, mu naught times the length L times the two wires, the currents, I'm sorry, mu naught times L times I1 times I2 divided by 2 pi d. If I took the same wire length L from both sides, the forces must be the same. Is there any other reason why they should be? Okay, I'm going to define again the same quantity as I defined before. And this is by definition is F12. So this is a linear force. So this is per unit length. Is going to be mu naught times I1. I2 to be more specifically times I1 divided by 2 pi AD. Numerically speaking, these two forces are the same. The direction of this force now has to point in the opposite direction. Let's argue why. So now the current is going up. The magnetic field is coming towards me. It's coming out of the screen. So in this case, the third, in this case, portion will point toward this way. So it's going to be in this direction. So indeed, wire 1 also is attracted toward wire 2. So when the currents are moving in the same direction, the two wires are actually coming closer to one another. This is an attractive force. Now, I found the magnitude to be the same of the two forces, and I found the direction to be opposite. Is there any other reason why that should be the case, other than this calculation? What, these two forces must be the same in opposite direction? Can you give me a reason why they should be other than this calculation, which is straight out calculation turned out to be the case? Come on, guys. You need to wake up. I'm waiting. Anybody? So let me repeat the question, okay? We calculated the force on wire 2 due to wire 1, and we found the value. Good? That's one thing. Then we calculated the force on wire 1 due to wire 2, and we found the same value, and the direction of the force is opposite to the first direction. Now my question for you, this is a calculation. That's what it yielded. The two forces are equal in magnitude but opposite in direction. Is there any justification for this one other than this straight out calculation? Why should they be equal in magnitude and opposite in direction? Goking, Miles, Heather, Sebastian, Eric, Pau. Okay. Zach suggested Newton's third law. Does anybody agree with Zach? Or have a better justification? Okay, Heather seems to agree with Zach. Is there any other reason why they should be? That is actually the only reason why they should be. Actually, once we calculated, because these are an isolated system of two wires with currents running through them, once I found the first force in magnitude and direction, then I know the second one must be equal in magnitude but opposite in direction per third law of Newton. The only complication was that L, and because that L, if it was off because one of them was longer and the other one was different, then the system is not really isolated in the sense that I have to take the infinity with it. So in the case when I take the unit force per unit length, they will be identical. And if I take the same length, they will be identical also, okay? And the third law is not violated in here, even if I take different lengths in this case, because then I have to explain the difference in size, okay? So that is really the point in here, that two wires, this is what the observation has indicated, two wires that are running different basically the currents in the same direction, they will attract. This is in like of what we have seen so far. If I have a positive charge, for example, and a positive charge, I know the force between them is actually a repulsive force, okay? Same thing with a negative charge and a negative charge. So like forces, they repel, okay? Like charges, they repel, I'm sorry. And also, if I have a magnet, for example, we have seen that with the north pointing on this side and another magnet with the north pointing on this side, these two magnets also repel. And if I have a magnet in here again, sitting next to another one with a south pole this way and another one with a south pole, this also repel. This result seems to do differently. If I have two wires with two currents running in the same direction, this wire is actually attract. Okay. Here is the question of the day. What happened in this situation? When the currents are actually in opposite directions? What do you expect happens? You have three choices. Either they do not interact whatsoever, or they repel, or they attract. So what do you guys think with two wires running currents in opposite directions? You have three choices. Okay, Daniel thinks they repel. Anybody else? Okay, so this is the question, one of the questions that we have to discuss it later on. Please be verbose. Do not put a single word in your discussion, okay? So two wires with currents running in opposite directions, they repel. But we didn't see the justification for it. We really have to understand what's going on in here, okay? I'm going to share with you the screen. Let me go down a little to draw this picture. So I'm going to choose this color again. So I have wires 1 and wire 2, okay? Wire 1 is running a current I1 this direction, and wire 2 is running a current I2 in the opposite direction. So I'm interested in seeing what's going on with wire 1. Okay, with wire 2 first, okay, due to wire 1. So I'm going to change the color in here a little bit, and I know the current in I1 is going up. So the magnetic field in this direction is always coming out, and in this direction it's always going in. So in particular, in this point, it's going in. So the magnetic field due to I1 is going to be inward in the position where I2 is. Okay, so in this direction, in this case, this is what I have. The magnetic field is it's inward. Okay. The current is downward. I'm sorry, the current is going down. That's the direction of the current. The direction of the magnetic field is into the screen. So the force in this case is away in this direction. So this is where the force is. So this is the force on wire 2 due to wire 1. Okay? So it's away from wire 1. Let's look at it now from the vantage point of wire 1 in term as affected by wire 2. Now wire 2 has the current running downward, raining down. So in this case, the magnetic field curves around it in the same way, counterclockwise, this way. So in this case, the magnetic field will be, again, due to wire 2, is going to be in this direction, is actually coming out. And in this direction, actually going in, same way, same like this one also. Particularly in this point in here, it's going to go into the screen. Now let's look at the force now. The force, the current is going upward. The magnetic field is, going into the screen, okay? So the force now is going this way. So again, the force in here due to wire 2 on wire 1 is pointing in this direction. So these two wires, they repel, and this is justification for it. Magnitude-wise, both of these two forces are given by the expression mu naught times the product of the two currents divided by the 2 pi times the distance between the two wires, where I'm assuming that this is the distance d. Okay, so this is the numerical value of my force, and this is again not a force. This is a Newton per meter. This is a linear force. This is not the total force. If I'm interested in finding how long this force, is I have to find out how long the wire is. Same thing, for example, if I have a 1 meter wire, probably I can carry it with both hands. But imagine if I have a mile wire, I have to have many people to come and carry it with me. I cannot carry a mile wire, no matter. I mean, let's say, for example, it weighs about a pound, a meter wire. Well, a mile of that is going to be weigh so much. I mean, it's going to be in the thousands of pounds, so it's not that light. So that's the same thing. So if I take, this is the force per unit length. So if the length is 5 centimeters, I have to multiply this one by 0.05. If the length is a mile away, I have to convert that into meters and multiply it by it. So this is a force per unit length. But the direction, now we understand it, okay? So this is something that we have hopefully we understand how this works. Any questions? No? So we're going to calculate now something that is critical for my electromagnet, the one I was demoing earlier. Let me see if I had another one, but I have a lot of junk in here, and I'm trying to get a newer camera in here to do. Here it is. I found it. Okay. Again, this is the purpose. So this is a better, cleaner thing than the one I crumbled. Okay, that messed up. So again, this is the electromagnet. That's exactly what this thing is, what we're going to be calculating next. So what I have in here, I have a wire. Can I change the wires connections maybe? Would this work better? I connect it in here, it's going to clap, and on this side, no, it's going to clap in here. So, yeah. I'm going to make the thing longer, but it's much easier to push this one inward than the other one. Okay. Let me find the red one now. Yep. These are called alligator clips, okay? So I'm going to connect the alligator clip to this one. So this is before the current is running through this. So I'm going to put it inside, and it's going to fall through because there is no magnetic field in here in it. So it should not really be held in place whatsoever. Obviously, there is a magnet on my laptop. Okay. But now I'm going to connect the current and have it. Come on. Have a current now. This is a 9-volt battery, so it's not a lot of current in here. So you see it, it's stuck in there. The minute I turn off one of them, I'm going to disconnect it. This thing should fall. Okay, apparently, oops, it fell. Okay, so that is an electromagnet. It's a current, it's a magnetic field that exists as long as the wire has current in it, okay? Obviously, the current, the strength of the magnetic field will be stronger right in the middle. So that's what we're trying to calculate in this case. So let me set it up so that we're good. So again, let's type in here and the thing in here. So circular loop. Okay. So let me draw the picture first. Okay. So what we have in this case is we have a loop. So this is how it looks like. Obviously, this is not realistic. As you can see, practically, there are the wires at the end in here. They're coming to make a connection. And so at the end, you have some connection. So technically, you should leave room for it. So there is no loop by itself. It's in the middle of space. So this is a theoretical loop. So what I'm going to do in here, I'm going to assume that it has a current running in it counterclockwise in the positive direction. So this loop, if I tilt it a little bit, this is how it's going to look like. So in other words, this is how you looked at it earlier. Now, if I tilt it, it's going to look like a little bit more of an oblique side. So if I completely reverse it, this is how it looks like. It looks like it's just straight out, up and down. So that's what I'm going to do, to look at it from as if it's straight up and down, to have a visual better than this one on it. So it's the same loop, okay? So it's not two different loops. I'm looking at it at different angles. So this is how it looks like right now, okay? When I look at it this way. The current is coming out in here, and it's going inward in here. wrapping around the loop, and it's running down in this section where it's going up in the other side. Does this visual, you guys understand it, okay? So in this direction, for example, the current is going this way, and the current is coming down in here, and the current is going up in there, so it completes itself. So that's how it looks like, more or less. I'm going to take a portion of this loop, it doesn't matter where I take it, in here, DL, okay? And DL has to be in the direction of the current. So my DL in here is somewhere in this picture. The reason why I'm drawing it in this way so that you guys have a better understanding of what we're calculating. So I'm gonna come into the middle, the symmetry, at a distance x from it, and I'm trying to find what the magnetic field in that point is. So from my DL, which is coming out, so the DL is coming out of the screen, okay, times I, of course. So IDL is coming out of the screen, and the distance between it and the point where I'm interested in trying to find the magnetic field, this is what R is. I'm assuming that this has a specific radius R. I think the book uses A, so let's use A. So the radius of this shape in here is A. So this distance up and down is A. So this is the distance A. So the radius of this ring is A. So R from this geometry clearly is square root of A squared plus X squared. The R hat unit is this way for that element, okay? So the magnetic field is both because it's given by, so this is a dB, not the whole B, okay? This is just a portion of it. It's mu naught divided by 4 pi, that's Biot-Savart law, times the I dl crossed with R hat divided by the distance squared. Okay, and we're going to integrate this expression. This expression is both perpendicular to R hat and perpendicular to DL. DL is coming out of the screen. So no matter what, the magnetic field must be on the screen to be perpendicular to anything perpendicular to it. Okay, so it's on the screen. Furthermore, it's perpendicular also to this R hat. So this is the direction for it. So I'm going to rise by 90 degrees, and this is my dB given by that expression. For this element, I'm going to basically find its X component, which is this. Let me remove R hat in here from this picture because it's really in the way. So this is R hat, by the way. So this is the projection in the X direction of the magnetic field. It also has this component in the Y direction. If I'm going to call this angle theta, this angle is the complement to theta because they add up to 90 degrees. And since this is the 90-degree angle, this angle also complements this one to 90 degrees. So this is also theta from the geometry, okay? So with that in mind, I have two components for this magnetic field. I have the one in the X direction, dBx, which is equal to dB times cosine of theta. And I have also dBy, which is dB times sine of theta, okay? And I need to find their sum. It's easy to argue that dBy is 0. I mean, by is 0. Why is that? Because dBy has this contribution, which is positive in this case, in the Y direction. So this is dBy. If I look at this element, for example, the opposite by 180 degrees, this is its R hat. The magnetic field is pointing this way, and it has the same X component, but the Y component is opposite and canceling it. So in other words, this is like a cone basically that is forming. When I project it in the Y direction, will give me 0. The only component that should survive is the X component. So let's ignore that symmetry for right now. Let's do the calculation blindfolded. I'm sorry. So cosine of theta from the geometry is clearly A over this R. Sine of theta is A times, I'm sorry, cosine of theta. Sine of theta is x divided by, sorry, I'm trying to think in terms of how we're going to argue that in terms of summing, because it's clearly the contribution in here from one side will cancel the other one. So I'm not really honestly going to bother with this expression, because at the end is going to be 0 when I sum it from 0 to 2 pi times a. Okay, the summation in here from 0 to 2 pi a. Because that's how the wire is, the circumference of the wire. The dl varies from dl when I integrate is from 0 to 2 pi a. This is the element on the ring itself. When I go around it, I would have gone a whole cycle. Okay, so the symmetry in here, I'm going to use a symmetry right now, will give me 0 for this contribution of this y component, because again, for each element, I have another 180 to it that's going to cancel this component, this vertical component, and the only thing that's going to survive is this y component, because both of them will have, I mean the x component, because both of them will have the same value. So I'm going to take this component in here and work with it. And the integration is going to be very simple integration actually. So bx, which is the whole b by the way, because the x component, the y component cancels, is going to be the sum from 0 to 2 pi a of 2 pi a of again mu naught times I times dl times r hat. Now I did already the calculation for the vectors, divided by 4 pi, and I have in here r squared. R squared doesn't depend on L. R squared is the same everywhere. It's always a squared plus x squared. A doesn't change, x doesn't change. So times again dl times cosine of theta, and cosine of theta from the geometry I argued to be simply a over r. So this is a over r. So the whole calculation will give me, because the integration of dl is going to be just L, evaluated between 0 and 2 pi a, that's going to be 2 pi a. So it's going to give me at the end of the day, basically, so let's move a little bit because I'm running out of space in here where to write. So this is a mu naught over 4 pi times I divided by r cubed times a times 2 pi a. So the 2 pi and the 4 pi cancel. Basically, it's gone. And I have an a into a, that's going to be a squared. So the magnetic field is going to be equal to mu naught times I times a squared divided by 2 times r squared, r cubed, which is a squared plus x squared to the power 3/2. Okay. So this is a big expression. What really matters in here is right in the center, because that seems to be the strongest. Actually, if I draw this function, it's going to drop quickly with a distance in here, especially when x becomes too large compared to a. This will become x cubed. So actually, this function is like this. The magnetic field on both sides drops whether you go this way or the other way, and it's maxed in the origin, and the maximum value is, which is right in the middle of the loop, is mu naught I. You will have x equals to 0, so you'll have an a cubed, and then you will have an a squared in the numerator, so it's 2a. So this is the strength of the magnetic field right inside the loop itself. Okay. Now, if I have more than one loop, like in this case, for example, I was doing earlier, I have a bunch of them, a huge number of them. Usually the label tells you how many. Okay. So in this case, the strength of the magnetic field is going to be mu naught times their number, because I have a bunch of magnets now, put one next to the other, times I divided by 2a. Okay. So this is simply the magnetic field that this was producing. Now, if I had a good device better than this one, I was able to measure the current in there. Current is much, much lower than even 0.2 in here, which is really actually 0.1. This was not moving at all for the current I was running earlier, even with this 9-volt battery, let alone the 1.5-volt battery. So the currents in here were running very, very weak. So if I have like I said, the multimeter that I'm waiting for today, I would be able to measure the current that is produced. As a matter of fact, if I can take the number of turns in here, and if I know the circumference of this guy's in here, so I know the length of this wire, and if I can assume that this wire is copper, so I can find the current in here that is running through it using R. Since I have V equal to 9 volts, I can use Ohm's law to find basically what the current is just by dividing by R. So the length times the resistivity of copper divided by the area, but I need to make some assumption here. This is a very, very small value in here. It's a fraction of a millimeter in terms of diameter for the wire itself, okay? This wire now is rated at gauge 28, which is even a smaller value than the one that I have in there. Actually, if you look at the different wires, they're gauged and they tell you exactly what each gauge is, okay? Any questions, guys? So I did this part in here, which brings us to Ampere's law, which is going to be very critical for understanding these things. No? So the big deal of this chapter, Ampere's law. Okay. So I'm going to go back into the wire that we did the calculation for. So wire I has a current I in it, produces a magnetic field given by the right-hand rule, where the magnitude of the magnetic field is equal to mu naught I divided by 2 pi times the distance where I'm at. So if I'm at a distance r from it, this magnetic field is going to come out of the screen, and this is the value for it, okay? What I'm interested in is the following. I'm interested in the circulation of the magnetic field. When I look at this wire from this point, this is how this looks like. Again, this magnetic field is going inward into this picture in here. So this magnetic field now, I need to get some real estate. So this is from that point, looking at it from the top, this is how the wire looks like. It's coming to me. It's coming out. So when you're looking at it, the current is coming to you, okay, from the top. Obviously, this is supposed to be a very long wire compared to the distance r, okay? So you're going to stand in front of it, and this is how it's going to look like. It looks like the current is coming to your dear eye. The magnetic field, distance r, is going to curl, okay? On a circle with radius r, it's the same magnitude. So if this distance is r, the magnitude of the magnetic field in here is always, first of all, in magnitude to be mu naught I over 2 pi r. As long as you are on a circle, this is its magnitude. There is no problem with it. Anywhere on the circle, it's the same magnitude, and it's tangent to that circle. So everywhere, that's the direction of the magnetic field. Okay, and it goes around, as I was describing earlier, following on, of course, counterclockwise, following the right-hand rule. And that is because the magnet is coming out. I mean, the current is coming out, okay? So what I'm interested in is this value. So I'm gonna go around on this path, which is really a circular path. So this is the path that we're trying to talk about in here, which is this circle of a specific radius r. And I'm going to take an element of that path, dl. Not the same dl we were talking about. The dl earlier in the formula was for the current, but this is just dl, just an element on a path in here. What I'm interested in, of course, the dot product of b times dl is going to be simply b times dl, because both of them are in the same direction, okay? What I am interested in this expression is the circulation, by definition, the circulation of the magnetic field over a closed path. This is a circle in this case. Is this dot product summed over, okay? So this is by definition the circulation over a closed path. So this is not a double integral. This is just a single integral, because what we're interested in here is just how does it circulate. The electric field does not circulate, by the way. If we were trying to do the electric field, we'll find zero circulation because it's always flowing. It's coming out, okay? It's always perpendicular to this path because the electric field is pointing this way. And if I'm going to go in a circle, they make a 90-degree angle. So this, for the electric field, this circulation is always going to give me zero. Okay? This is for the electric field, okay? Over a charge, of course, if I'm looking at it from the charge. Now, that is the electrostatic field. Okay, in this case, I'm looking at that of the magnetic field. The magnetic field definitely have a circulation, and we want to find it. So let's find it in here. This is a special path. So the magnetic field in magnitude, first of all, in this dot product simply reduces to the product of the two quantities because they are parallel in this case. So the circulation in this case over this circle of BDL is simply BDL, the integral of over the same circle of BDL. B is constant on the entire circle. As long as R doesn't change, B stays the same. So this will come out of the integral, and I'm going to just find basically the circumference of a circle. Because when I add the DLs from my starting point and I come back to the same ending, so this is simply going to be B times the circumference. And the circumference of this circle is 2 pi r because it has a radius r. And B is given by this expression, mu naught I divided by 2 pi r. So the 2 pi r upstairs and downstairs cancel, and I would be left with simply equal to mu naught I. So this circulation over a specific path, which is a circular path in this case, is independent of R. It's constant quantity is equal to permeability of the medium. This is assumed in the vacuum times the current that is being enclosed in this case a positive value. So the circulation in this case is given by mu naught I. I'm going to change the path a little. Instead of a circle, we want to have any path. Okay, so we're going to go through a different geometry a little bit. So again, we're still looking at the current from the top. So this is how it looks like coming out. The magnetic field is still circulating anywhere. So if I'm in here, this is how the magnetic field looks like. If I'm in here, this is, of course, it drops like 1 over distance. So if I'm in here, this is how the magnetic field would look like. Okay, but the closer I am, the value itself is always equal to mu naught I over 2 pi r. But if r is different, then the magnetic field will change. So I'm going to assume this path is going this way and then curves this way, and then it's going to come out this way. So this is not necessarily a circular path in a sense that it's not a circle, but it's a path nonetheless. Okay, okay, that encloses this current. Any point in here, obviously I drew this one wrong. Okay, I'm sorry. So it's supposed to be parallel to this. At any point in here, DL is parallel to B. But B is different now. It's not the same B. At this point, it's stronger than in here than in there, because this drops like 1 over distance. Since this is closer to the wire, this should have stronger magnetic field than this point. Okay. The product of BDL is still BDL always in this case. Okay, as long as I'm going in there. Oh, obviously you're wondering, maybe, wait a minute, hold on. Maybe I'm going through the original path. Let's do the original path in here. Let's take this point in here, okay? Okay, I'm gonna take a weird point in here, okay? So if you guys don't mind. So I'm gonna break it in here. Let me erase these points in here. Oh man, Control Z, erase the whole thing. I'm going to take this point in here to be DL in there, okay? So that the magnetic field now is still this way, but the DL is making an angle with it, okay? Let's assume that there is an angle in there. Well, the magnetic field in this case is always along the direction, the angular direction as you're curving. It has no radial connection whatsoever. It's always curling around. So the magnetic field now, if I'm going to write it as a vector in here, it has 0 times r hat. It has no radial direction, and it has only along the theta hat, along the angle, the direction that you're changing. So in this case, is going to be simply equal to that value, which is mu naught I over 2 pi r. Okay, and the azimuthal direction and the angular direction. The DL now has components. In this case, it's all of it along the angular direction also. That's why that product resulted in there. In this case, DL has a component inward in the radial direction, but that's going to give me 0 anyway. Because there is, when I do the dot products, it's going to multiply by 0. The other value will have no 0. The azimuthal direction, because I also have direction in the changing in direction. So as long as I'm going in or out, that does not contribute to the dot product. Because the magnetic field has no in or out components. All of its components is only when you change direction only, okay? So in this sense, the dot product will always result into the product of the magnetic field times the displacement in the angular direction only. And the angular direction is going from 0 to 2 pi. So once you complete the whole cycle, you're going to go 2 pi direction. With how much you go up in terms of distance, because you move away from the wire, you're going to drop with the magnitude of the electric field, the magnetic field. Because the magnetic field is inversely proportional with R, and the displacement will increase with R. But the two increases and the decreases will be exactly enough to cancel one another. The only thing that is going to stay is the fact that you're going to add a 2 pi in the whole cycle. So at the end, the 2 pi from the denominator and the whole integration will cancel the 2 pi. And any increases in DL because you're moving away, or any increases because you're coming down, or any decreases because you're going up, will be canceled with the changes in R, okay? Because if you move away, R increases. But the magnetic field will decrease with like 1 over R. If you're coming inward, R will decrease for the DL, but the magnetic field will increase because the magnetic field is proportional to 1 over R. So this increases and decreases will cancel, and at the end, the denominator will be canceled. At the end, the path integral also will give me the same quantity. So B over any closed path, now not necessarily a circular path, closed path, of BDL, because of the properties of how B changes with distance, it decreases like distance, and L increases with distance, I mean the path that you're going to move. Obviously, this is how the picture that I'm talking about in here. If this is the displacement, let's say this is R1, this is how much path you have moved in the same angle, because at the end you're going to go 2 pi, okay? In the same angular displacement d theta. So this is the path you're going to move. It's going to move R1 d theta. But if this is the distance, you're going to move R2 d theta. Once R increases to R2, this displacement increases proportionally to R2, okay? With the same displacement d theta. So as R increases, the displacement will increase. In the same time, the magnetic field in this point is 1 over R1 times 2 pi. And in this case, it's 1 over R2 times 2 pi. Since the displacement now is proportional to R2 and the magnetic field is inversely proportional to R2, this will cancel. Same thing in here. R1 and R1 d theta will cancel. So at the end, what survives is the integration over d theta from 0 to 2 pi. And the 2 pi will be just enough to cancel the 2 pi in the denominator. Okay, so this the integration also should give me the same thing. I'm sorry, no 2. Will just give me mu naught I. So no matter how I look at it, the circulation of the magnetic field over a closed path is going to be mu naught times the current. Now let's look at it from a different point in here. We're almost there, okay? So the argument is almost there. I have a current that is coming out. Again, I'm looking at it from the top, and I'm choosing this path now, okay? Where the current is not inside. Well, if I do this, it doesn't matter where I start from. Let's say, for example, I start in here. Let's call this as the x-axis and call this one is 30-degree angle. Remember, if R increases, dl increases, but the magnetic field decreases, so the R effect is canceled. The only thing that matters really is the theta. So if I go from 30 degrees and increase to, let's say, for example, 60 degrees, and then come back down to 30 degrees, and come back to any value in here, negative 12 degrees, for example, come back to 30 degrees, the boundaries of integration are going to be from 30 degrees to 30 degrees. No matter what I have in here times the theta is going to be 0. Because there is a theorem that you guys did in calculus that if the boundaries of integration are the same, then in this case, the value of the integral is going to be 0. Because no matter what this yields, an antiderivative of f of theta, evaluated between theta naught and theta naught is going to be f of theta naught minus f of theta naught. This is 0, okay? So that is how the theorem works in calculus. This is not the same though. I start from 30 degrees and I come back to 30 degrees, but then in going after 2 pi, I don't come back to 30 degrees, I come back to 2 pi plus 30 degrees. That's why the difference in here is 2 pi. Whereas in this case, actually the difference, because you come back in here, this is where the calculation is. This is where you're starting from. So you start from 30 degrees, you go up to 60 degrees, and then you move down to some value, and then you're negative, and then you come back. You didn't do a whole cycle. You guys understand? You didn't go through this cycle a whole. So you went from 30 degrees, you went to, let's say, for example, 60 degrees, and then you came back to 30 degrees to this point, and then you came back to negative 12 degrees, for example, and then you went back. So this integration did not really complete the whole cycle, whereas it did in this case. It went through a whole cycle and gave you 2 pi. So if the current is outside of the loop, where you're doing the integration, then in this case, there is no magnetic field. So the circulation of the magnetic field is 0. So the circulation of B dl in this situation over a closed path not enclosing currents. This path does not enclose any current. It's 0. There is only one thing that is left, and we have the theorem before us. And that is when I have more than just one wire. So if 2 wires, for example, I have wire 1, and I have wire 2, and I have this closed path. Then I can assume that the circulation of, if wire 2 does not exist, the circulation, I'm going to call this one path in here, I'm going to call it P. Over P, excuse me, of B1 dl is equal to mu naught I, 1. And the same thing, I'm going to assume that in this case, that if wire 1 doesn't exist, then wire 2 is equal to this circulation. If I add these two quantities, I'm adding on the other side the algebraic value, which is just mu naught times I1 plus I2. This equals to the sum. This is a property of the same path because the path doesn't change. This is P also, of B1 plus B2 times the same element of integration, in this case dl. And I'm going to say that these 2 wires combined, they produce the magnetic field B1 plus B2. So what I'm arguing in here is the magnetic field due to both wires is going to be just given by this expression. Can anybody remind what this thing is? Can anybody tell me why I make this justification from here to here? There is something that allows me to do this. Does anybody remember what this thing is? I took wire 1 as if wire 2 doesn't exist. I took wire 2 as if wire 1 doesn't exist, found the magnetic field of each case, and I said the total magnetic field must be the sum of the two magnetic fields due to each wire as if the other wire doesn't exist. Does anybody remember what this thing is called? What's justification for it? Come on, guys. We use that in electricity, in electric fields. So this is the thing. Find the magnetic field of wire 1 as if wire 2 doesn't exist. Find the magnetic field of wire 2 as if the wire 1 doesn't exist. And argue that somehow the two together is actually what the magnetic field is for the whole thing. This has a name. Does anybody remember what that name is? Yes, Alex. It's the superposition principle. Okay? It's by superposition. Again, it's a principle because it's not a law, because there is no justification for it and how to basically why it works, but it does. So this is this by superposition. That is again the same, the second question of the day. This is by superposition. So please, when you're writing this stuff, be a little bit verbose. Do not say just by superposition. So assume that wire 1 is by itself. Find the magnetic field. That's exactly what I did here. Assume wire 2 is by itself and find the magnetic field. And then argue by superposition that the total magnetic field is just sum of these two vectors. Okay? So that is the second item of the discussion today. Superposition principle is really a very powerful principle, which we don't know how it works, but it does its trick. Okay, so this is Gauss's law now. I mean, this is Ampere's law. The circulation of the magnetic field over any closed path. This is any closed path is equal to mu naught times the I enclosed. By convention, the I enclosed really have to be very careful with it. It's positive when it's coming out, and it's negative when it's going in. So the current, you have to be very careful, okay? So if the two, for example, if one is coming out and one is coming in, this has no circulation whatsoever. At any given point in here, the whole circulation should be zero. I mean, there is probably a value for the magnetic field in there, different than the other. But if you are interested in the circulation of the overall over any closed path, that should be zero. So if I have this wire, for example, this has I, and this has I, in here, obviously, and in here, you're saying, okay, this point in here is closer to I1, to this I that is coming out, and it's pointing downward, okay? Whereas this one is very far away from it, but it's very weak, okay? Then you're gonna find points in here where this one is actually going counterclockwise, stronger, and the other one far away from it, and it's weak, okay? And when you add them up, it's like adding, for example, a positive 3 and a positive 2 and a negative 2 and a negative 3. So at the end, you're going to find 0. This overall has 0 circulation. Granted, on a given point, the value could be positive 3 and a positive 2, depending on how far you are from them. If you are on this side, it's going to be a positive side. If you are going to be on this side, it's going to be a negative side. And overall, the whole circulation is 0. So this is an algebraic sum. You have to be very careful with it. This is an algebraic sum. Just like when we were doing Gauss's law, where we said that the flux of the electric field over a closed surface, any surface actually, of the electric field times dA was equal to the charge enclosed over epsilon naught. There is a little bit of shift. First of all, mu naught is not in the denominator, but rather it's in the numerator. And the second is that the idea of charge enclosed or current enclosed is the same thing. This is algebraic value. And here, we're looking at positive charges and negative charges and basically adding them up. Granted that if I have a positive charge on this side and a negative charge on this side, the electric field on this side is going to be very strong, whereas, I'm sorry, it's pointing inward. The electric field on this point is going to be very strong, whereas the electric field, first of all, it has a different direction, and they don't have to have the same. So it's going to be, I'm sorry, it's going to be away from it, and it's going to be a lot weaker, so it's going to be this much. In here, it's going to be the opposite. It's going to be a lot strong in here, but super weak for the other one. But when you add this number and this number, they're going to give you, at the end of the day, value that is 0, okay? And you add up these two values. As long as the charges are the same. If the charges are not the same, then it's positive if the positive charge dominates. It's negative if the negative charge dominates. Same thing in here. If the currents are not the same, then the circulation is not necessarily 0 in this case. It's not going to be 0 in this case. If this current in this wire is stronger, then in this case, the overall circulation is going to be positive. If the current in this side is stronger, then the overall circulation is going to be negative. In other words, this is actually netting a clockwise magnetic field. Whereas in the first case, where this one is stronger, it's netting a counterclockwise circulation of the magnetic field. It's a lot, but I'm hoping that you guys have some at least visuals to help you understand this chapter a little bit, okay? So that is Ampere's law. In the case of how to use it to find the magnetic field, let's use the simple case that we just did. In other words, what is the magnetic field, for example, of a wire that we just argued in here? And it will result in that same case. Let's say, for example, a cylinder. And try to find the magnetic field inside a cylinder with a uniform distribution of current in it. So I'm going to take a wire in here, and as I move away from the wire, remember they have a finite distribution in here, J, and this is the current enclosed, is J times this area. So I'm at distance R from it. So the current enclosed is going to be I equal to J times pi R squared. Okay, so the J is uniform in this case. On the other side, the circulation is still 2 pi by argument of symmetry in this case also, 2 pi R times the magnetic field. This times mu naught should give me the value of, now here pi it cancels with pi, and also R squared cancels with R, and the magnetic field is seen to increase with distance, mu naught J divided by 2 times R, okay? When I'm outside, it's going to be just mu naught I divided by nothing. I mean, divided by 2 pi R if I'm away from it. So the magnetic field in this situation of a cylinder, so this is a cylinder with uniform. Remember, we were dealing with uniform stuff in the lecture when we were doing the electric field, when we had the row uniform, and then come exam time, you guys did not have a uniform, you had a non-uniform. So be expecting something similar, okay? So a cylinder with uniform current distribution, current density. So J is uniform in this case. That's why J times the area will be simply the current. So the current enclosed is just this much enclosed, not the one that is outside. That's not going to matter. So in this case, inside is going to increase as 1 over distance. Increase as distance, I'm sorry. And outside, because outside we just calculated it's going to be I over 2 pi R times mu naught. So it's going to decrease exponentially. Okay. And this is R, the radius of the cylinder. Okay. So this is some of the applications that we can have, okay? I want to close this chapter. I know we still have about 10 minutes, so I want to finish this chapter with discussing the magnetic materials, okay? Again, welcome to the afternoon session for today for Physics 4B. We're going to just show you basically part of the things that we'll be doing in this lab. I took a paper clip and I opened it. What I'm going to do to it is basically I'm going to make it in such a way to hang a wire off of it. Part of the lab is you're going to estimate its diameter. Okay. You can Google it basically. This is a paper clip that I formed into this shape. Okay. I have another one. I need to do the same thing to it. By the way, you can Google how to make electrical motors, and you should be able to also find a lot of instructions in there. As I said before, the lab instructions are not 100% ready, but they should be, and I'm going to post them. Hopefully either tomorrow, before Wednesday anyway, you should have them. Here is the second wire in here. Basically, this is the ultimate code in here. I'm going to have them basically sitting next to one another where I just made the loop. But again, the loop has a problem right now because I need to, where did I put it? Where did I put the loop here? Hey, did anybody see where I put the loop in here that I just made? Basically what I did was I took about 1 meter long of this wire here. Okay. Took 1 meter long of it and I wrapped it around a D-cell battery. D-cell battery will be perfect in this case because you can have a nice, so many turns in here, okay? But then I need the sandpaper, and I know I have some. I'm going to go and grab them. I think they're in the other room. And sand this portion, because ultimately this is how this would look like. It's going to be sitting on top of this wire, okay? So that's how it's going to be sitting. For me, I have actually this one in here that I'm going to use, but this is only for 1.45 volt battery. You don't need to have this. This is a battery holder. Okay, you don't need that. You can use what is it, Play-Doh or or tape. I mean masking tape if you want to tape it so that these two are not they're independent like this basically somehow. Make sure that these are leveled where the hanging points are, okay? So when you do it, you have to be very careful with this configuration in here, and that's it, okay? So that is in terms of how it did not rest. Let me see what's going on. Now it's sitting, okay? So this is the startup. I'm going to put the battery in here. And after I put the battery in here, of course, it's not going to work because I did not sand these portions in here. There is no connection between the wire and there is no current running through these wires, okay? So it's not going to work. And I need a magnet. And I think I have some pretty good magnets in here. And that's part of the lab too. Sorry, where is this strong magnet? Where did I put them? Yeah, they are here. Okay. Let me remove this. I think this will do. Okay. So this is a configuration for the motor that you'll be making. Okay. So it's similar to this one. The current right now is not running. That's why you don't see anything. The reason why I really need to sand these portions, once I sand it, I'm going to basically record this one and add it to the lab instructions because there is no connection right now between the two of them. I'm afraid if I use this pliers, okay, I'm going to cut through them, through the wire, and then it becomes useless. In other words, I have to make another one. So using sandpaper, you can do it, and then it's going to run, okay? It should run. So this is part of the lab that we're gonna do today. As an alternative to that, I already have a motor in here, electrical motor, if I can find where it is. I mean, you wouldn't believe how many things I have in here. It's not even funny. Where is it? Where did I put that motor? Here, okay. I have already a motor, okay, that if I connect it to a power source, in this case, a battery, I don't need a magnet. It has already a magnet inside of it. Okay. So if I connect it to a power source, it should start running. So right now, it's not connected. And that is the principle of the lab today. I don't know if you saw it or not. Okay. So this is not moving. But once I connect it, it should start spinning. Okay. So this is the principle of the motor. Okay. Part of the lab is can you hear me, Miles, or was it before or right now? The sound issue. Okay. So yeah. So basically, what I was demoing to you is my construction for the motor. Okay. Actually, it should not be hard at all. The thing with it, and that's where you run to, you can use plastic, basically cup holder, okay, where to put the these things in here. Here's the problem that you're gonna run to if you're gonna make it, and I need you to make it, okay, because you're gonna be making this one. If not, then you're going to write a report into what happened. Okay, on calculating the torques and seeing things like that. Here's the problem when you do it with a paper clip. Right now, they seem to be hanging, so it seems to be working fine. So alternative to that, I mean, they were going to fall. So what you get going to do in this case, I have played on the other side, is to have a masking tape and hold them in place. Even with that, the minute you put the magnet between them, there is a problem. These two wires are made out of iron, so they start to be attracted to it. Okay, attracted to the permanent magnet that you're, because you need the permanent magnet between them. So you can see that this wires and the magnet, they will start to interact. So there is a problem with that configuration. Any kind of cardboard should work, okay, as long as it's thick enough. Because again, what you want to do is adjust the heights in here so that when this one, you're going to be working against gravity. You're going to be working with the force of gravity, so you need to deal with that. So you need to put them as symmetrical as possible, because you would want to create a strong enough torque. Remember the torque from class, it's mu cross B. Let me get that thing there in here. So the torque is going to be mu cross B. So tau for the magnetic field is mu cross B. And mu numerically is simply equal to IA. And the current that is running through it is going to be dependent on how long the wire is and depending on how these things are. So if I connect it from here to here, this is where the current is. So it's going to go all the way, come back, and come in here. So this is the calculation that some of you who are not opting for the actual to doing the lab and uploading their own picture, their own image, building the motor, then I'm not their image, their own video actually, with them themselves working on the motor and struggling through it and getting it going, they need to fill out the calculations actually. So the current will come from the battery, goes through this point, goes through the loop that I was showing earlier, goes through the other, come through the other leg, and come back through close the circuit. So we have a current that is running through the loop, this loop, okay? That depends on the length. I took about a meter length of this copper wire. And if I Google basically how big is the gauge 32, because I use gauge 32 wire. Okay, what is my wire? Mouse. Okay. My screen now is not responding. The whole thing is frozen. Do you guys hear me? I can't really go anywhere right now. Let me hit escape now. I'm sorry. Okay. Even with this mouse, it's not working. Control Alt. I'm going to do some stuff in here to see if what happened to my computer. Do I have something in here in the way? Yeah, okay. It's better now. Okay, so let me find the value of 32 gauge. 32 gauge. wire diameter, because we need that diameter for the calculation. If you are using different gauge, if you're using 28, which is also could work, you need to find the diameter for it. Okay. Actually, there is a list in here for all the gauges. One thing you need to note for this gauges in here. Oh man, they have them in inches. I need them in centimeters. Okay. Okay, let me copy this page, copy the image, save the image as. Okay, I don't need to save it. I can copy it, paste it to you guys. Copy, save image, copy image. Let's go back in here. Let me paste the image in here to see exactly what I have found. Because it gives you all kinds of gauges, you have to be very careful. Since we're talking about this lab, you need to know the difference between these things in here. Oh, I need to have it bigger. Can you guys see this image in here quickly? Okay, so basically, anything that says AWG size, that is what I was talking about, the gauges. In here, it doesn't show me anything that is anywhere near what I need. Okay, these are high wires. These are very thick wires. Okay, up to gauge 20. Gauge 20 is similar to the one that I bought actually from Home Depot yesterday or the day before. And this is gauge 20 wire. So as you can see, it's clearly much, much thicker than a gauge 32 wire. Okay, you can see the difference between them. So this is a gauge. Let me hold them both closer to one another. Okay, the red one is gauge 32 and the white one is gauge 20. The gauge 20 is the one that I bought from. So now, since this does not give me, so it's going to give you the metric size, okay, in millimeters. This is basically different standards, different versions of them. This is all the 20s that they have in there. Forget about that for right now, since we don't have anything that is of what I want. So let me quickly in here get gauge 32, exactly the one I am using. So if you're using a different one, like gauge 28, then you need to use gauge 28. What's the number for it? So right now, I need to go back and see what is gauge 32 wire look like. Gauge 32, according to this data that I have in here, is 0.2 millimeter. It's like the hair, piece of hair. So the radius is going to be, in this case, 0.1 millimeter, 0.1. That's 10 to the negative 4 meters. So if I'm doing the calculation on this one, so gauge 32, for my case, I need the R in here. I need the R. The resistance for this wire, the one I am using, the resistance is going to be rho for copper times the length of the wire, which I said is about a meter, okay? I didn't measure it, but I should really measure it, divided by the area A. The area A is the one that is related to the gauge, pi times R squared. Remember, R in this case is going to be 0.1 times 10 to the negative 3, that's millimeters. So it's going to be 10 to the negative 4. So this area A is pi times 10 to the negative 8, really, when you square it. So this resistance in this case, why is it so high? So let's say, for example, it's a meter long and it's copper. What is the copper? Is it 1.72? So the rho for the copper, 1.72 times 10 to the negative 8 times the length, which is 1, divided by pi times 10 to the negative 8. That is the area. So the resistance is going to be roughly 1.72 divided by pi, and 1.72 divided by pi is roughly about 0.5 ohms, okay, slightly more than 0.5 ohms, slightly, yeah, 0.5 ohms. So that's the resistance that I have in this wire, okay, that I have in there. Did I use it backward? No, that's correct. You need to verify the calculations. Time is the cross section. Time is the area A. This is the area. So there are two A's in here. You have to be very careful with them. This is calculation of the resistance, so that has to do with the gauge. This one is this area actually. The torque now has to do with this area. Okay, so technically I should find the diameter in here that I have measured. One way of doing it is wrapping, because I use a D battery, D cell battery. So is wrapping a string around the battery and measuring its length. Okay, so if I wrap around this string, so it's going to be a few centimeters. So that's basically the area. That is another pi times r squared. That gives me the magnetic moment of this loop. But remember how many I have in here? I have to multiply by them. I have 1, 2, 3, 4, 5, 6, 7 of them. So I have to multiply this number by 7 in my case. Yours may be different, okay? So now I have tau. The magnetic field is the problem now. The magnetic field, because I'm using a magnet, I have to really use go by what the industry says. For this one, it was saying, I think, like 400 Gauss, okay, which is 400 times 10 to the negative 7, which is 0.04 Teslas, okay? So that is the value that I have to go. So that's going to create a torque now that needs to be compared to mg times r. I have to estimate the value of this one. Again, if I look for the gauge of this wire in here, I know its length, I know its, I know the density of copper. I can find what its mass is based on the length, based on the gauge, basically pi times r squared times the whole length, that gives me the volume, times the density of copper. Now I have the mass for this wire, okay? I have the mass for this wire multiplied by G multiplied by R, again, in order to find the maximum gravitational torque that I need to have to overcome. So now I have the magnetic torque compared to the gravitational torque that I need to overcome in order to have this motor running. So here is how the configuration would look like. You have a bunch of wires in here that are connected to this way. You have, again, this connection. Where you hang the actual wire. And you have, in this case, I use the 1.5 D cell battery. I could use a 9-volt battery to get more kick, to get more current, okay? So in this case, I have the battery. Doesn't matter the orientation. Okay, either 1.5 or a 9-volt. Okay, where I make the connection in here is going to play a role in here. This is iron, so I need to measure this whole length in here, and the diameter is going to be about a few millimeters, so it's going to be something times 10 to the negative 3 squared. So it's going to give me another resistance in here plus this resistance. Now, if I have an ammeter, and I don't know if any of you have a multimeter at home, and they are used by electrical. By the way, I received mine today. Here it is. I just received it between classes. Actually, I checked out, and it checks outside, and it was there. So this is the multimeter I was talking about in here. This is a very nice device. I got it from Amazon, I think, for like $20. This one does a lot of things for me. This is unlike the ones that we have in the lab. The old ones, the ones that we have in the lab, we can do a DC volt. We can do an AC volt. Basically, what we need for our case is a DC voltage, because this is the direct current. That's the one that we're using. And we can also do the DC amp and the AC amp for them. Okay, both of them where you turn it. And we can also use them to measure the the resistance. Right now, it's measured either for the voltage when I connected these two ends in here, either for the volts or the resistance. That's what I have them in here for. However, this one does more. It does the capacitance, which I was surprised because I didn't know that it does that. But I saw when I was buying this one that it does also the thermometer, which comes with this thing in here to measure the temperatures too. So the thermometer. Did I say thermometer? Yeah, it's a temperature basically. Yes. Okay. And it came also with another adapter that I saw also for it to measure actually the properties of the PNP and NPN transistors, which is part of a lab that we will be doing down the road, namely for diodes. So this is basically the device that we can use to find the current. So what I'm saying in here is if you have one of this, it's very nice because it should be able to help you measure that current. You don't have to, especially if you're doing it at home, you can measure the current. Sorry? Yeah, the one I bought in here is $20. It's a very, very nice one. Actually, yesterday or the day before, I don't remember exactly now. Time is when I went to Home Depot, this same thing. I mean, something exactly similar to it, or actually not as good as this one. I think they have it for like $40 or something, twice as much from Home Depot. So I'm not, I mean, Amazon is not paying me whatsoever in here, so that you guys know. But if you're at home and you want to get into electronics, this is something it's nice to have, okay? And actually, you can have it for your household stuff too, okay? You can check things and do things like that. So I had a lousy ammeter, which was, this is a voltmeter actually, and the ammeter is here, okay? The ammeter that I had with a kit that I also bought, this one, the maximum it's supposed to measure is 3 amp. And it can go supposedly up to 0.6 amps. And if you look at the characteristics, it's not really going to measure very weak currents. What this is good about versus the ones that we have them in the lab. The ones that we have them in the lab, you start with a higher value of the voltage and you start coming down, okay, so that you don't burn the fuse inside. The reason why you start with a high voltage, let's say, for example, the voltage, for example, is 100 volt, and you put it on the lower volt in here, let's say, for example, it says up to 10 volts, but it's 100 volts. So it has the potential of bringing a huge current, especially when we're dealing with the currents in here, that it could burn the fuse in them, okay? So this one also has the 10 amps and the microamps. Can you believe that? This is like extremely it's like a extremely small basically currents and milliamps. So this is supposed to be very sensitive, but it adjusts automatically for me. I don't have to do anything. So when I was measuring the resistance, by the way, that I had in my circuit earlier today, and I was showing you that resistance turned out to be 5 kilo ohms. I didn't have to adjust anything. It automatically read the number for me and gave me the value for it. So it's really very nice, okay? So this is something, again, if we are in the lab, you guys will experiment with it and you play with it and you had your fill with it. So if you're into electronics or computer stuff or playing with things like that, this is something that you would want to have, okay? So again, this is basically what I want you to do. Wow, they're expensive. Yeah, I mean, I know, in the old days especially, okay? I'll send you the link, no problem. So, okay, Daniel is asking for the link. So let's, if anybody else is interested, let me find it in here. Go into my Amazon stuff in here and usually it's under orders now. Okay. Okay, here is the link for it. Okay, I know Daniel asked for it. And if you guys are interested, this is something that is nice to have. Okay. $22, I think, to be specific. Wow, It went up. They put them on sale. For right now, I think it's showing, you know those days when they have things for sale? So it's actually, now you're going to get 10% discount. I don't know if you guys have that or not. I don't know. Sometimes when you buy something on discount, the next time you look at it, they immediately raise the price on it and they change it. They say, okay, the discount was over. You bought it on the special. Now it's not there. Anyway, watch for these things. They're very nice tools to have. Okay. Anyway, so that's one thing. So that's part of the lab. The other part of the lab that I didn't finish the writing and I actually show you partial of the things that you need to be doing so that we have at least some things that are going on. And I promised earlier that we're going to do a problem, so we're going to do that too. So let me show you. Let me first of all stop sharing the screen and share with you what you're going to be doing so that we, at least part of the lab. This is not the full lab, by the way, okay? So again, things that has to go with the, I'm still basically, I didn't even finish the writing of the instructions. Anyway, so here is the question that you're going to be asked. Oh, you're not seeing it, I'm sorry. Share. Okay, the Word file. I'm still working on it. Okay. So again, part of the background stuff that normally asks about these things, question about the magnetic monopoles, okay? And here is the part of the activities that you will be doing. You will, if you don't have a horseshoe, this is how it looks like, okay? It's color-coded, blue on one side and red on the other, okay? Blue on one side and red on the other, okay? Same thing. This is a bar magnet. You will need that. Blue is always south, N is for north, the red is north. So for your case, this is, what is it? The north, this is the south, north and south, okay? The same thing, at some point you will need a ring magnet, okay? Permanent magnet. Again, on one side, it's one color. Here it's a blue. On the other side, it's a different color, red, okay? On one side, it's north. On the other side, it's south. Okay, so that's again the three things that you'll be needing. Okay, you have a horseshoe magnet. So remember, on one side it's a pole, on the other side it's not. So what you're going to be doing in this case is drawing the field lines. The field lines will always leave the north and end in the south. Okay. So I suppose if this is north, this is how the field lines will go. In between them, they go straight out, okay? When it's, and they starts to curve in here. And in here, it's curving this way. So in here, it's leaving, and it's ending up in here. Now, for the bar magnet, on one side, you have a positive, not positive, I should say, here. You have them labeled, okay? North and south. Here. There will be some questions about these labels too. I mean, if it's not labeled, how would you find out if it's north or south? Okay. I don't know if these guys are labeled or not, but here is blue and here is red, okay? So again, you're gonna be drawing the field lines. Again, they will emanate and end up in the other side. In here, it's actually a different situation, okay? You have a bar magnet, so the curling on one side is this way and the curling on the other side, actually this way, and the curling on the other side outside is this way. So you have to really be, you have to imagine how this thing is working in here for the bar magnet. This is a bar magnet where it's a raised, oh no, so ignore this instructions in here, I'm changing it, okay? As I said, this is just drawing the magnetic field. Here is where it becomes interesting, when you have two bar magnets next to one another in this way. So in here, you have a north facing south and a north on one side and the south on the other, okay? On this side though, you have south versus south and a north away. So you're gonna draw the magnetic field and how to draw them. On this side, you have two magnets, two bar magnets, side by side, north next to north and south next to south, and you know what happened in this case. There is a repulsion. So you need to think about these configurations. Again, so what was the other question in here? Why is this? So this is a very thin configuration. And again, this is flipped in here in this case, so you need to do that. And in here, again, the field line for a single disk magnet, very thick, okay? And in here, you have them opposite to one another. So if I'm doing this one in here, so you guys are looking at them like this, okay? So basically, this is the configuration. And the last configuration, this is basically how you're looking at them, both of them facing north. So the other side is the south, the one that doesn't have the label on it. So this is some of the things we'll be doing in this lab, in addition to the electromagnet, which is something that I demoed already in lecture, okay? What happened to the electromagnet if I flip up the polarity, for example, in here? So I have, this is an electromagnet. Electromagnets, they are temporary magnets in a sense. They don't have really magnetism per se, because if I put them, by the way, I have also the magnetic needle, and that's part of the question that you're going to be asked about it, which way it's going to point, which way it's not going to point. So here I have a bar magnet, and I'm going to, again, a lot of these things you really need to, so which side is attracted to it, okay? Is it the red side? Again, I'm bringing, so here I have a bar magnet. So if I flip it around in this case, what happened to the needle, okay? So again, if I flip it around, oops, in this case, sometimes you have to give it a kick. Even in practice, you have to give it a kick. Even if you are outside trying to find your way home, you have to tap it a little bit to get it to work correctly, okay? So if I take this one now and study the magnetism that this thing produces, it's not basically where I point it in here, it's actually following the Earth magnetic field. So if I reorient this one this way or that way, it's not going to impact it. However, if I run a current through it now, trying to connect it to the 9-volt battery. Okay. Now it has a current running through it. As you can clearly see, I connected the whole thing to a 9-volt battery. And let's see here now. It's going to be a very weak magnetic field now. Okay. Okay, it's going to change it following it. I don't know if you see that or not. When I bring it closer, it has to be very close from the center. Again, typically this should not interact with the wire, but with an iron piece. But if I cut the current right now, as I did earlier in the class, this will fall. As a matter of fact, I just touched it because this one has a loose connection. The current was just quickly dropped to 0, so that this will fall. Again, this is the electromagnet. Okay, I have another electromagnet in here. This is actually, I don't, it's not even labeled. It has so many turns in it that I don't know exactly how much charge is running through it. But again, there's a problem with this one. How am I going to connect it if I don't have, maybe through the alligator clips? I have 2 of them in here. Okay. So let me see if I can get the current running. Again, this should not attract anything. There is no magnetism in it whatsoever. So right now, if I put it this way, it's not going to do anything. But if I run current through it, I have to be very careful with this one in here because both wires are loose from both sides. So I need to really bring them together, hopefully with this alligator clip. And the other side also similarly with another one. Okay, I think if I lift it up a little bit, let's see here, is it still connected? Oops. It's very weak current running through this one in here apparently too, or it's loose. I think it's not connected. Anyway, I have to have a better connections for this one. Sorry guys. Okay. Yeah, it was lost from the other side. The wire came from the, here is the trouble I ran into with this one in here. This is a very short connection from the battery side versus the one that is in here. And this is actually a thicker wire. So it's not running well. Anyway, these are some of the stuff that we'll be doing in this lab. The main thing that I'm going to, when I finish the instructions, which I'm going to share with you guys soon, is to have you guys build your own electromagnet. Short of doing that is explain all the calculations that you need to do in order to find the torques, as I explained, for the the magnetic torque and the electrical torque, the gravitational torque, and the fact that you have to have strong enough, which I was not able to do earlier with the other wire, with this wire, because this wire has tremendous, it's super thick, so it has a lot of inertia in it, and I couldn't get it running with the super weak currents that I was running with this in this wires. So I didn't have enough strong enough magnetic field to overcome so that's the 20 gauge wire that I got from Home Depot. So that's not good. That's too thick for the purpose of what we're doing. So that is part of the lab, of course, if you're going to opt out of the actual building your own motor. Now, when you're building your own motor, you have to tape everything. You have to tape the stage when you're making the actual loops and count them, okay, because you will need to know how many roughly they are. I did about 7. 7 is good enough because I took a meter long wire, about a meter long. Actually, I just basically estimated to be about a meter. I need to be accurate if I'm doing the calculations. And also I took I wrapped it around a D-cell battery. If you use the smaller cell batteries, it's going to work. Now, if you don't have a D-cell battery, you can still make it. You don't have to do that. So you just wrap it very carefully with your hand and over a small section. This wire is too big. I mean, this cup is too big. If you're going to run it, try to make it smaller or through a something that is not too big, okay? So make your own loop. And then grab a magnet. This is a magnet that is according to basically the place I purchased was about 400 something Gauss, which is typical number for this kind of magnets. I have a stronger magnet, but that's another thing I'm into to worry about. Anyway, so that is something you will need. Connect the current, and now give it a kick for the motor to start, and you should start it running. You at least have to run it for about a minute, okay, to be able to consider it a motor. So you need to run the clock on it and see that the motor is going for at least a minute. Now, because of the connection, sometimes they drop for the wiring and the current drops to zero. Because of the battery starts running out of juice, that's one thing, especially if you experimented with it a lot, and I've been doing that, which means that I always have to check the voltage on my battery to make sure it's still good. This battery, according to this voltmeter, is supposed to be 9 volt, okay? So what is it? Oops, switch the polarity. So the reading was going in the opposite direction. Sorry about that. Right now it's giving me 7 volts, okay? So it's supposed to be 9 volts, but I've been using it right now. It's reading 7 volts on this thing in here. So, and you have to watch for it because it gets hot, especially the 9 volt battery. If you keep on connecting it over a long time, it's going to be super hot because of the current that is running through it. I mean, especially if it's high enough current, okay? So that is some of the things you're going to be doing in this lab. Any questions in terms of the things? I know you will need the lab instructions, and hopefully you will have it no later than tomorrow evening because I need it also for the other class too. So I have to finish that as soon as possible for you guys and the others, okay? So this takes care of 2 labs actually. takes care of the magnetism lab and also the DC motor lab. So this is going to account for both of them. Okay. So this is in terms of the activity. So from now on, I expect you guys to go and start working in terms of trying to get your things going if you want to do that. And hopefully you'll be successful enough in it. Now, if it doesn't succeed, that's fine. That you're going to get full credit for it because that's part of the lab, trying to experiment with it. So hopefully down the road in your own plain time, you can get it going and working for you guys. Okay. So you're going to not miss on that. So that's part of the lab activities that we have. If you were in the lab, you will be provided with materials and you will be actually, I did it in the past where we actually compete and making these things work. So that's one thing. The other thing, as I promised, is, unless you guys have a question for today, is with this lab board. The other thing that I promised we should do today is actually do calculations. So let me go into the book quickly. I want you guys to look at problem 75. I already mentioned in lecture today, we did the calculation using Ampere's law. This is problem 75 from chapter 28. A long, straight, solid cylinder oriented with its axis in the z direction carries a current whose current density is J. The current density, although symmetrical about the cylindrical axis, is not constant. Remember, I always say that you're going. So let me type the problem in here for you guys so that we have that. Let me share the screen first. So the so we have a cylindrical wire basically. It's in the z direction. It has a current density, and that current density is not uniform, is not constant. Okay, so the current density is not the same everywhere. So it's actually a variable function. So let's see here. So the current density is given by J equal to B over R. So it's in the K hat direction. It's in the Z direction. So B over R it's B over R times the exponential, and it's in the K hat direction just from the get-go because it's a vector. I have to remember that. That's from the chapters 20, I don't remember, 25 or 26, I think. Times R minus A. So it's going to grow exponentially or decrease exponentially, I should say, divided by some quantity in here, which is called delta. Divided by delta. So let me remove this thing out of the way in here. So let me rewrite this expression. The magnitude of the current is B over R times exponential of R minus A over delta. Okay, so that's problem 75 from chapter 28. Okay, so that's the if you guys are following. This is not part of the homework, by the way. This is a separate one. When R is less than A, but when R is greater than A, it's 0. There is already a problem with this question in here in terms of the question itself. Hopefully you guys are looking at it and you discover that there is an issue because it says this is for R less than or equal to A, but for R greater than or equal to A, J is equal to 0, and that cannot be true because if R is equal to A, this is exactly A minus A, which is 0. Exponential of 0 is 1, so this should be B over R, which is equal to B over R. That's the value. But then they said that it's 0, so this is cannot be true. So what I'm going to do in here, I'm going to assume that this inequality is not correct. So it's greater than A, period, end of the story. So this comes at an abrupt value in here. So drop. So the current density is 0 outside. and inside it's this finite value, which is b over a. At r equal to 0, this is an exponential of negative something. So it must have been this value. Is it? No. Is it increasing or decreasing with r? When r increases, yeah, it's increasing from a smaller value all the way here, and then it drops drastically to 0. So this function is increasing exponentially of some sort, but then it decreases. So this, in this case, so it's b over a times exponential of negative a over delta. Okay, so it's going to increase exponentially, but then suddenly drops to 0. That's the point I'm trying to make in here with this problem. So once you have that, you let's read the questions now. It's saying where the radius a is equal to 5 centimeters. So they gave us a. R is the radial distance from the center of the cylinder. From the cylinder axis, B is a constant equal to 600 amps per meter. So A is given, B is given, everything is given in this problem. And delta is a constant of 2.5 centimeters. That's just a characteristic in here, delta. Let I naught be the current passing through the wire. So I naught is equal to the whole current. So this is just the current density. This is not the whole current, by the way. So I naught is the whole current. Remember, I naught is equal to the integral of J times dA. Okay? J and dA are in the same direction. J is in this direction as a vector, and the area dA also is in the same direction. So the dot product is really their product, because cosine of 0 is 1. But of course, we're integrating from 0 to a. We have to be very careful in here. So this integration is over the area. So in other words, theta varies from 0 to 2 pi, and r varies from 0 to a. So this is the area where the current is going through. This is basically where the integration also needs to be. Okay? So that is, and the element of area in this case is r d theta times dr. In other words, this is basically the element displacement in the radial direction is dr, and in the angular direction is r d theta, and this is the element dA. It's dr, the radial displacement. So we're having some origin somewhere. So d theta. So this is the angular displacement d theta. This is the displacement corresponding to that angular displacement, which is r d theta, and this is the radial increases, and this whole thing is dA, the element of surface, and obviously the element of the surface is throughout the entire area in here. So the question they said is express. Let's look at the expression question exactly. Obtain an expression for I naught in terms of B, delta, and A, all of the constants. So basically do the calculation. Calculate this integral. Carry this integral. So I naught is equal to B over A. The integral, again, you have to be very careful for A varying from 0 to A, whereas theta varies from 0 to 2 pi. Of the current density. The current density depends only on the radial direction. It says B over R, B over A. I'm sorry, there is no A in here. It's B over R. So I have 1 over R exponential of R minus A over delta times R dr d theta. R and R cancel. And basically, I'm left with the integration of delta d theta, which is 2 pi. And the integral of dr exponential, so I need to make a change of variable, and we're there. So I naught then is b times the integral. So I have 2 pi, and the 2 pi has to do with the integral of d theta. And I'm going to do now the integration over r, which is exponential of r minus a over delta times dr. Exponential in here comes out of the integral for the negative a over delta, and I'm left with the integral of dr over the delta over the r over delta. So I'm going to make a change of variable where r over delta is equal to u. That means du times the delta is equal to dr. And with this change in variable in mind, this is how this integral would look like. Stop me, guys, if you think I'm going too fast. 2 pi times b times the integration of the exponential, first of all, on negative a over delta, the integral from 0 to a, and when I do the change of variable, it's exponential of u times delta du. The delta come out of the integral, and the exponential, the integral of the exponential is the exponential itself. I'm sorry, when I do the change of variable, the boundaries of integration change. Since r is equal to delta u, so this boundary of integration becomes delta a. Okay, I'm sorry. So the integration over u, sorry, is going to be a over delta. I'm sorry, it's a over delta because u is equal to r over delta. So if r changes from 0 to a, u changes from 0 to a over delta. Anyway, so if I do this, then I naught is equal, remember I got delta in here from the change of variable, so it's 2 pi b delta times exponential of negative a over delta times the exponential of u is exponential of u between 0 and a over delta. Well, the upper limit will cancel this coefficient, and the lower limit will have that same coefficient. So this will be 2 pi delta b times 1 minus exponential of minus a over delta. Plug in the numbers if you like, okay? So this is I naught expressed in terms of b, delta, and a, okay? Does this make sense to you guys? The whole thing resides into this thing in here. How the current and the current density are related to one another. In other words, J is by definition the gradient actually of, I cannot really, it's the derivative if you wish with respect to J, or if you like, this is the definition for the current. It's the sum over a surface, not over a volume or over an element of things. So basically, this is the current density. How is it distributed over a surface? So this is the definition of the current overall. So that's the question. Does anybody have any question about this thing in here so far? So it gave you basically, the question was express I naught in terms of B, delta, and A. So this is the total current carried by this wire. All I did in this case is note of the fact that J and A, delta dA are in the same direction. So this is the element dA. And it's also perpendicular to, parallel to J. So they must be in the same direction. So the dot product of these two vectors is the same as their product. And I need to express dA in polar coordinates though, and on the plane because it's an area. So it's r dr d theta, okay? Because if I take a vector r, vector position r on a plane, this is the vector r. This vector can increase by dr in magnitude, that is, in the radial direction. Or if I change orientation by d theta, it can increase in that radial, in that angular direction by r d theta, and this is in theta hat direction. In general, I can move in the r hat direction or theta hat direction. So this is the overall displacement, if you wish. It's a vector sum of these two vectors. The area is just the product of these two, okay? Once I have that, then, and the d theta and d changes independently of dr, and r changes from 0 to a, whereas d theta changes from 0 to 2 pi, and that gives me basically, this is how we actually got that expression, if you wish, for the area of a circle. For the area of a circle, yes. This will give you r squared over 2, and this will give you 2 pi integrated from 0 to 2. So the area of a circle is pi r squared. Okay, so that's how we got that result from. Anyway, so this is that calculation. Any question about this problem? Again, I'm trying to do quickly an example in here for you guys. And this is really, if you guys have, if you have any questions about these things, please let me know. So this is part 1 of the problem. Part 2 of the problem, it says in here, using Ampere's law, derive an expression for the magnetic field in the region outside. So since we are outside of the cylinder, similar to when we do actually Gauss's law, this is we need to choose, instead of using Gaussian surface, we're going to choose now. So this is my wire. So we are somewhere in here in a region greater than A. So what I'm going to do in this case, I'm going to choose so-called Amperian loop. Amperian loop is a made-up loop similar to the Gaussian surface. So it's a loop that I'm going to assume is just a circular loop of radius r, where r now is greater than or equal to A. So it has to be greater than A, actually, I'm sorry. The current enclosed is the one I just calculated, I naught, okay? And if I go around circulating in this direction, I can argue by symmetry that if the current is going up, so therefore in this case, the circulation is going to be in this direction, inward, and it's coming out in here. And the circulation is going to be 2 pi r times the current in this case, which is, I'm sorry, 2 pi r times the magnetic field in this case, outside, must be equal to the current enclosed mu naught I naught, and the magnetic field is simply equal to mu naught I naught over 2 pi r. So that answers that question. And remember, guys, when we do problems together like this ones, you guys are accountable for them also. Even though they are not part of the homework, they may be in the exam too. So when we do problems outside of the homework set, so those are also part of the review problems for your class too. Okay. And the reason why I'm mentioning that is because it's critical that you guys pay attention to this point in here, that this is actually when I was doing the lecture, I mentioned the fact that the current density was constant. So when I did it earlier in the day, when we were doing lecture, it was a very simple example that you guys should not have had difficulty with it, because all you have to do is multiply J by the area, and you're done. You're there. But in this case, J is not constant. And what I mentioned that then there is that the examples we do them in the book, usually they start with J being constant, usually start with rho being constant for the charges. And then at the end, when it comes to exams, chances are you will end up with non-uniform distribution of currents and non-uniform distribution of charges. So this is an example that is actually a non-uniform distribution of currents. So you need to know how to do this thing. So that's really how real life sometimes presents itself. As a matter of fact, it presents itself in far more complicated fashions than this, in a sense that even this one will become too ideal situation for a real life situation. Okay, so we calculated this one. Now the second part of course, some of you are already guessing, has to do with the fact to calculate the current density enclosed at a distance less than. So I'm going to go back into the wire. But now we're inside the wire. We are in a distance less than A. So now R is less than or equal to A. In that situation, we have a problem because this is the area enclosed. So the current enclosed is only this one. I'm going to do the same calculation, but instead of finding the total current now, I'm going to find the current enclosed. So I enclosed again is going to be the integral from 0 now to r, okay? And the integration over theta is from 0 to 2 pi still. And the current density is still given by B over R times exponential of R minus A over delta times the element of surface now. And the element of surface is R dr d theta. The dr and the r cancel, okay? I could have chosen a different variable name in here other than r, because the integral is an indefinite integral as far as r is concerned. So in the end, that's sub for it, but it's the same thing. I'm going to find the antiderivative at the end. So again, the same idea as before in terms of this calculation. First of all, I'm going to have 2 pi coming from the integration of d theta from 0 to 2 pi. And I'm going to have the b out. And I'm going to have the exponential of negative a over delta. And I'm going to have the integral from 0 to r now, exponential of r over a times dr. Again, I'm going to make the change of variable of du, u, equals to r over a. In this situation, this variable varies from 0 to 0 to r over a. Okay, so at the end, that's basically what we need to do. dr in this situation becomes a du. So I need to pick up an a in here. Did I forget an a in the calculation in here somewhere? I'm sorry, delta. There is no a in here. I'm sorry, that's where the error is. So that's a delta. So this is actually a delta. This is actually a delta. And this is actually a delta. Hopefully you guys caught this mistake in here. Okay. So I enclosed then is 2 pi b times exponential of minus a over delta. And this integration is from 0 now to r over delta, exponential of u times, again, now I picked up a delta, du. And delta comes out because it's a constant. It's 2.5 centimeters in this problem. So I enclosed is going to be 2 pi b exponential of minus a over delta times delta in here times the exponential of u evaluated between 0 and r over delta. Okay. Obviously, if I multiply it by the exponential, this expression becomes I enclosed is going to be 2 pi b delta times open parentheses exponential of r minus a over delta minus exponential of minus a over delta. This is the expression that we find for the I enclosed. They say specifically for this problem to express it in terms of I naught. Here is I naught. This is this expression. So what I'm going to do is 2 pi delta b must be equal to I naught. So in other words, I over I naught, I enclosed over I naught is going to be I enclosed over I naught. The 2 pi delta will cancel from both sides. There is a 2 pi delta in here, b, and I have 2 pi delta b in here. So they cancel, and I'm left just with this exponentials divided by one another. So I'm left with the exponential of r minus a over delta, exponential of minus a over delta over the other ratio of exponentials, which was exponential 1 minus the other exponential. So this one was 1 minus exponential of minus a over delta. So basically, this is how this expression, when I take the ratios. So in here, I have in actuality how this expression is. As a matter of fact, if I have multiplied by exponential a over delta everywhere, this will cancel, and I will pick up another one in the denominator, and the other one will cancel, and the I enclosed, if I do this algebraic operation, will be I naught times the ratio of exponential of a over delta minus 1, exponential of r over a minus 1. Okay, I just took the common denominator, and here I multiplied by exponential of positive a plus delta. So from here to here is multiplied by exponential of positive a over delta. That will become 1, and the other one will become 1, and that one will cancel, hence I don't write it in here, but I have to pick it up again in here. So this is I naught in terms of, I enclosed in terms of I naught. It depends on R, of course, okay? If R is 0, I have no current enclosed because this will become exponential of 0, which is 1 minus 1, I have 0. If I have R equals to, delta, I'm sorry, in here. If I have R equals to A, then exponential of A over delta minus 1 over exponential of A over delta minus 1, that is I naught. That is the whole current enclosed. So if R is equal to A, I'm back to the situation where we started with, okay, earlier. So this is the current enclosed. Now they want to find the magnetic field in this inside region here. So how much is the magnetic field in this point, B? So again, I'm going to use a Gaussian surface, which is actually a circle, whose radius is R. So on the left-hand side is going to be the circumference, which is 2 pi R, times the magnetic field must be equal to mu naught times this current I enclosed. Since I have already calculated it, so this will be just the expression for the magnetic field is going to be mu naught I naught over 2 pi R times the exponential of R over A minus 1 over the exponential R over delta, I'm sorry, over the exponential of A over delta minus 1. Okay? So this is the whole problem. I did not plug in a single number in here, but in the problem they gave you what delta A, which is 2.5 centimeters, what they gave you what A is, which is 5 centimeters. So you know the ratio in here is E squared, okay? Because 5 over 2.5, that's E squared minus 1. And they gave you specifically what the value of B is, 600 milliamps, I think, per meter or something like that. So they give you everything in the problem. So technically, you should be able to get everything in here, this problems. The final expression doesn't have B in it because B and delta are actually enclosed also in the how we found I naught. So we need to find what I naught is, okay, in amps. So B is 600 milliamps per meter. So you're going to multiply it by this one. And you're going to, once you plug in, you're going to find all of the numerical values, which I didn't really do. I'm hoping that you guys will carry on the calculations. Okay. Does this make sense to you guys? It's a lot of calculation. I agree. Okay. But it's only two basic ideas in it, so that we are together agreeing. The first thing is how J and I are related. J and I is the sum over an area of JDA. Okay, and the area in this case, since it's cylindrical surface, it's basically a circle. It's pi. I mean, it's pi r squared if the whole area. But I'm not talking about the whole area. I'm just talking about portions of it. So I'm going to do the calculations, but it's basically r d theta, because I have to integrate it over a non-constant term. If J was constant, then I'm going to just multiply J pi r squared. But J is not. So I had to integrate in here. The good thing about this problem is it has 1 over r in it. That cancels the other r, and basically you're just doing an integration of the exponential, which should be easy enough for you guys to do. Okay? And then follow the steps. So once we find the current enclosed, then we go back into Ampere's law. That's the second idea. The second idea says that the circulation of the magnetic field over a closed path, which is in this case 2 pi r times b, because I'm taking the path to be exactly a circular path. So it's the circumference times b. And the reason why it has to be exactly the circumference because the magnetic field is uniform. It's the same throughout in here. I'm making the argument based on symmetry because it doesn't change. So if I rotate my wire one way or the other, the magnetic field should not be impacted. So it comes out of the integral times 2 pi r, which is the circumference. So on one side, it's easy. We don't really have to do a calculation. On the other side, which is mu naught times the current enclosed, that's what we really have to do. That's where we ended up doing the calculation. Finding that I enclosed, okay? That's where we had to do the J, R, dr, d theta. And d theta everywhere is just 2 pi when you integrate it because there is a symmetry again. That's cylindrical symmetry. So the only integration we ended up doing actually in all parts of this problem were the radial integration because the current changes with the radius. It's not fixed. It's not the same. The current density is not fixed and the same throughout the entire radius. It changes as an exponential of r over delta divided by r because you have 1 over r also in it. So it changes exponentially, actually. It increases right on the border and then it shuts off. Of course, there is no current outside of the wire. That's what it means. Okay, the wire is the only place where the current exists. That's why you have current density. So this is a problem from chapter 28. I need to introduce chapter 29 because we're going to do it on Wednesday. Okay. So any guys, any questions about this problem? Any questions about this problem? Okay, good. So let's go into chapter 28 to discuss it briefly. I'm not going to do chapter 29 that is today. Okay. So let me share with you the screen. So again, this is exactly what chapter 29 was. It's this thing, okay? In a sense, this current creates a magnetic field. That's chapter 28. So the fact that when I run a current through this one, I have a magnetic field. That's fine. That's good. So current, which is actually due to an electric field, actually, there is an electric field between the ends of a battery in here. This is the positive, this is the negative. So in this case, there is an electric field. If I connect wires in here, that's electric field. When I connect it through this thing, that is why current is moving, actually, because it follows where the current field is. So if I connect this one into this end and the other one to the other end, I have a current flowing, and the only reason the current is flowing is because there is an electric field. So what Mr. Faraday and other people actually were looking at that point, could the other way around work? Could the magnetic field create an electric field? So that's the whole premise of it. So what they did was, they tried with magnets to see if they can create a magnetic current in this wire. So now I have a wire. If I connect the wire straight out to an ammeter, for example, to this ammeter, would I see a current running through this wire if I put next to it a magnet? Well, it did not work. So what happened was, they needed actually to vary to move the magnet in or out, or move the wire in or out. One of the two. So a changing magnetic field creates currents, create an electric field, if you wish. Okay. So that's the result. That's the premise of what chapter 29 is. So the whole idea for chapter 28 was, an electric field creates a magnetic field. Chapter 29 looks at the other question around, backward. Can a magnetic field create an electric field? And the answer, yes and no. Yes, it can, with a condition. And the condition is the magnetic field has to be moving. It did not need to be for the electric field to be moving. All you needed was a stationary electric field to create a magnetic field. For this situation, you need the magnetic field to be in motion to create this electric field. And that electric field is not is a very bad electric field, actually, that we create. Okay, so that is really the essence of this chapter. Why is it bad? Because this electric field, you will see, the one that is created by magnets, is unlike any electric field we have seen so far. In other words, this electric field does not diverge. Its divergence is zero. Divergence of the first electric field was equal to the charge density, basically divided by epsilon naught. This one does not diverge. Actually, the other one does not circulate. This one circulates. So this is everything the other electric field was not. The electrostatic electric field was a very well-behaved and understood electric field. This is not an electrostatic electric field, the one that is created by magnets. Okay. Yet you will see it has a lot of its applications, and one of them is actually how electrical currents come to your house. So that's how we actually make currents to begin with, and this currents happen to be the AC currents. Okay. So there will be a huge problem for us later on when we try to argue Kirchhoff's rules, because the whole idea behind Kirchhoff's rules relied on the electrostatic fields, the fact that the electrostatic derives from a potential. So we have a potential, we have a voltmeter to measure that potential, and hence the way also of finding where volts and drop of potential and resistors and capacitors and things like that. This one does not derive from a potential. So technically, we should not be able to talk about circuits when it comes to this weird looking electric current, electric field, because it's non-electrostatic. It's not based on the idea that it derives from a potential. It is supposed to be diverging. It's not. It's not supposed to be circulating. It is. So everything the other one is not, this one is, the other one, everything the other one is, this is not. So that's going to be a major problem. So how in the world we're going to save the day and talk about AC circuits, because they're dominant, they're everywhere. All the electronics is based on AC circuits, at least before you get into them, before you get into other things. So for example, on any power supply that you have in your connected to your computer or anything like that, it's actually an AC circuit. Yet Kirchhoff's rules need to be altered enough for us to work with them. Now, if you're going to be majoring in any physics major, you really should worry about this whole discussion. If you're going to be an engineer in any engineering field, it doesn't matter what it is, including electronics or electrostatics and everything else, you really don't care about the discussion, because you're going to apply Kirchhoff's rule and you're going to be in great shape, okay? That is really the only thing I'm going to say. Being a physicist myself, I'm going to worry about it, and we have to really make a whole argument on it, okay? As I said before, if you are going to be an engineer, you're fine. You don't worry about it. You just apply Kirchhoff's rule as if nothing happens, okay? So that's the whole thing with chapter 29. At the end, we're going to summarize everything, okay, for this chapter, okay? So this is it for today. We're not going to, I'm going to assume that you guys are going to start thinking about your motors and how to make them, waiting also for the instructions for the lab. Any questions? Okay, very good. So I'm going to see you guys. I'm going to stop recording first, and I'm going to see you Wednesday.